Alright, so to get started in Chapter 2, Section 3, we're going to get started with solving some application problems involving linear equations. So here's our first example. It says, find a linear equation to solve for the unknown numbers. One number is 11 greater than another number, and their sum is 35. Find the two numbers. So a good strategy for when we're trying to resolve any type of word problem is the very first thing we should always do is identify what it is we're trying to find and then give it a name and a symbol. So our goal is to solve for some unknown numbers. So let's let x be the first number. And if that's the case, we have a clue about the other number. It says one number is 11 greater than another number. So if x is the first number, then the second number is 11 greater, so it must be x plus 11. So now we have each of our two numbers, and we were able to do that because we named the first thing. So since our first number was x and we know that the other number is 11 greater than the other, we can just take our first number and add 11 to it. Then our last bit says that their sum is 35. So we need to add them together, so that's x plus 11, and their sum is going to be 35. So now we can solve for each of these two numbers. So we collect our like terms and we get 2x plus 11 equals 35. We minus 11, and we get 2x is equal to 24. And we divide by 2, and that gives us x is equal to 12. So our first number is x equals 12. And then the second number would be, well, it's x plus 11. So if x is 12, that's going to be 12 plus 11, which is equal to 23. And a quick check, 12 plus 23 is indeed 35, and 23 is 11 more than 12. So this indeed is the solution to that equation. All right, so to resolve this, we're going to do the same thing. So we're going to have our first number be x. Then x plus 20 is the other number. So then we would have the sum of those numbers, so x plus 20 is equal to 66, so that gives us 2x plus 20 equals 66. We minus 20, we minus 20, and that gives us 2x equals 46. Divide by 2, and we end up with x is the same as 23. So then the other number is going to be 23 plus 20. So 23 plus 20 gives us 43. And those are the two numbers. All right. So let's move on to our next example. So before we get started on this example, we do want to talk about a model, and that model is called simple interest. So the simple interest model is I is equal to P times R times T, where I is the total interest, P is the principal or the starting amount, R is the interest rate, and T is going to be time. So for our simple interest model, we have our total interest, our starting amount, our interest rate, and our time. Well, now let's go ahead and look at this next example. So Martine has $4,000 invested in two separate accounts. A low-risk account pays 2% simple interest, and a high-risk account pays 8% simple interest. If he made $230 in interest last year, how much money is in each account? So for these types of problems that are called mixing problems, in this example we're mixing money, I like to make charts. I find it simplifies the process. And making a chart or a table to help me work on this problem, I'm going to have a column in the table for each variable in my model. So I have my interest, I have my principal, and I have my rate and my time for my simple interest model. And then I'm going to have two different accounts. So I'm going to have account 1, I'm going to have account 2, and then we're given some information about a total. So I'm going to end up with 3 rows in this table, and I'm going to end up with 4 columns. So we have our table. So now we need to figure out what it is we're looking for. So we have our goal at the end. It says, well, how much money is in each account? So I'm going to let X be the amount in account 1. And if that's the case, I know the total amount in both accounts, which I can fill in here, is $4,000. And if I have X dollars in account 1, well then how much money would have to be in account 2? Well, this is one of those times where we can use our intuition and remember that variables are just numbers that we don't know yet. So if we're not sure, we can pretend the variable is a number to help us figure it out. So if I had $1,000 in account 1 and I know I have $4,000 total, well then how much money would have to be in account 2? Well, that would be $3,000, and I got that by going 4,000 taking away the amount that was in account 1, which was 1,000. Well, if I have X dollars in account 1, then account 2 would have to be 4,000 take away X. Because whatever amount I have in account 1 is X, it can't be in account 2, so I have to take that much away from the total. So that allows us to fill in those values, and I put them in the wrong column. So let's move them out of the interest column and into the principal column. So we had X, 4,000 minus X, and 4,000. So then we have our low risk account. So right here, I'll call that my 2% account, and we can never put in a percent. We always have to change our percent to a decimal, so 2% as a decimal is 0.02. And then we have a high risk account, that'll be account 2 is 0.08. And then we are told if he made $230 in interest last year, well that's a total, so that's going to go here. How much money was in each account? Well, it seems like we're missing some information from our table, but there's some implied information in words that isn't given in numbers, and that is the interest last year? Well, the length of time for last year would be 1 year. So now that we've filled out our table, we'll notice that our model tells us that I, the interest earned, is equal to P times R times T. I can use these values to fill in the interest in account 1. So it's going to be X times 0.02 times 1. So that gives me 0.02X. And similarly, I can do the same thing for account 2, P times R times T. So 4,000 minus X times 0.08 times 1 would give me 0.08 times 4,000 minus X. So now, I know the interest in account 1 is 0.02x. I know the interest in account 2 is 0.08 times 4,000 minus x. And I know the total interest earned is 230. So that allows me to set up the equation, the interest from account 1, which is 0.02x, plus the interest from account 2, which is 0.08 times 4,000 minus x, is equal to 230. All right, so now we resolve our equation by distributing into our parentheses. So we have 0.02x plus 0.08 times 4,000, so 0.08 times 4,000 gives us 320. 0.08 times negative x is negative 0.08x is equal to 230. So we collect up our like terms, so 0.02x take away 0.08x is negative 0.06x plus 320 equals 230. We minus 320. We minus 320, and that gives us negative 0.06x is equal to negative 90. We divide by negative 0.06, and we divide by negative 0.06, and that gives us x equals negative 90 over negative 0.06, and we get 1,500. So if X was the amount in account 1, and account 1 was the 2% account, so then the 2% account had $1,500, and the 8% account had 4,000 minus 1,500, so that's going to be $2,500. And this, once again, was the 4,000 take away the amount that was in account 1. So then that would be the amount in each of our accounts. All right. So we're going to move on to our next example. But once again, before we get started on the example, we need to talk about another model. So this one is the distance model. And the distance model is d equals r times t, or as I like to call it, it's our freeway model, which says if I get on the freeway driving 60 miles an hour for 5 hours, how far did I go? Well, it's 60 times 5 would give me 300. So in this model, d is the distance, r is our rate, which is just really our speed, and t is going to be time. All right. So example 3, a suspect in a high-speed chase enters I-8 eastbound at 60 miles per hour. 12 minutes later, a highway patrolman enters I-8 eastbound at the same location at 75 miles per hour. How long until the officer catches the suspect? Okay, so I'm going to use the same strategy that I used in the previous problem. So I'm going to make a table, but first we need to figure out what it is we're trying to find. So how long until the officer catches up to the suspect? So let's let T be the amount of time the officer, or the highway patrolman, is on I-8. So then, using the same strategy that we had above, D is equal to R times T. We're going to make our table, but in our table this time, we're just going to have the suspect and the officer. So my table's only going to have 2 rows in it this time and 3 columns. So let's fill in the information we know. So the officer has been on I-8 for T minutes. So that was what we named our variable. We say that a suspect in a high-speed chase enters at 60 miles per hour, so that's going to be their rate, so 60. 12 minutes later, the highway patrolman enters I-8 eastbound at the same location at 75 miles per hour. So now we have T, but the question we need to ask is, well, who has been on I-8 longer, the officer or the suspect? Well, it would be the suspect. He's been on for 12 minutes longer, so he would be on for T plus 12. So using the same strategy that we did above, we now know that D is equal to R times T, and R times T here would be 60 times T plus 12 for the suspect, and for the officer it's going to be 75 times T, so we get 75T. So then for the officer to catch the suspect, they must be in the same place at the same time. Because if you're going to catch someone, you have to be in the same place at the same time. Well, that would mean then that their distances must be equal. So our equation this time is going to be 60 times T plus 12 is equal to 75 times T. So then to resolve this equation, once again we open our parentheses using the distributive law to get 60T plus 60 times 12, let's see, 72 with a 0, so 720 is equal to 75T. And then we resolve by minusing 60T, minusing 60T, and we get 720 is equal to 15T. And so we go 720 divided by 15 gives us 48. So T equals 48. So in this problem, it would take 48 minutes for the highway patrolman to catch up to the suspect. All right. So the next one's going to be a U-try, but once again, we're going to need some formulas for a rectangle. So the area of a rectangle is given by area is equal to length times width, and the perimeter of a rectangle is P equals 2L plus 2W. So in terms of a diagram, we have our L and we have our W, and we have our area and our perimeter for said rectangle. Equation, so P equals 2L plus 2W, and area is equal to length times width. We're given that the length is 12 more than the width. So we'll start with an equation that we know isn't true, which is L equals W. We know that's not true. In fact, we're told that the length is 12 more than the width. So this one is bigger. So to make that statement true, to make it balance, I have to make the other side of the equation bigger. So then if I add 12, since L is 12 bigger, then that would make our equation true. So then L is equal to W plus 12. And if I were to put this into my perimeter equation with the value of our perimeter, which is 60, we would end up with the equation 60 is equal to 2 times W plus 12 plus 2W. And we open our parentheses by distributing, so we get 60 equals 2W plus 24 plus 2W. Collect our like terms, so 4W plus 24. So we minus 24, we minus 24, and that gives us 36 equals 4W. Divide by 4, and we get W is equal to 9. Well, if W is equal to 9, then L is 9 plus 12, so it is 21. So then our area is going to be our length times our width, which is 21 times 9, and 21 times 9 is 189. So the area would be 120 or 189 square centimeters. All right. So that is the